Okay, we just did an in-class example on this copper alloy, and we went through the steps how to solve the resultant elongation, how to find the total length under the load, and how to find the load after recovery. And now I want to change this problem a little bit. Here I want to change the load here. I would like to change this load. Instead of using 200 micropascal, I want to use maybe 400 micropascal. And in the problem statement here, I want to get rid of this assumption. Okay, now let's look at this modified example problem. And I want to ask you, how can we solve the first question? We just need to find what is the resultant elongation delta L when you apply this 400 megapascal load, tension load. And here my question for you is, can we still use the equation, which is Hooke's law, sigma equals epsilon times E? Can we use this? Okay, like I stated previously, this equation can only be used under elastic deformation, and which means and the deformation has to be within in the elastic region, has to be smaller than the yielding strength. And but do we have a load smaller than the yielding strength? Since we don't have this assumption, we know here we have a larger tension load, and we do not really know if this load is exceeding the yielding strength. We do not know the deformation caused by this stress. It's either under plastic region or elastic region. Therefore, you cannot use this equation. If you use this equation to solve this problem, and you will get totally wrong answer if you don't do the justification to use this before you use the equation. Alright, and if you have such a problem, what should you do? And the good way to solve this type of problem is to find what is a stress strain diagram for this alloy. And let me give you this a sketch stress strain diagram here. Let's assume this is a stress strain diagram for this copper based alloy, and okay, if this is a given stress strain diagram for this alloy, and you can check the tension load before to do any calculation. Actually, if you have the stress strain diagram, everything will be easier. You don't even need to calculate using the equation. And here the load is 400 megapascal. And if you come back to the diagram here, 400 megapascal corresponding to a point that is beyond the linear region, right? That means the deformation under this tension stress, it's a combination of elastic deformation and permanent or plastic deformation. And from the diagram, we can read out what is the strain under this tension load right away. So here, the intersection on the x direction, on the epsilon axis, and will tell you what's the strain under this 400 megapascal load. Let me label the number here. Here, I will just assume all the numbers may not necessarily represent this alloy, but let's assume this is a diagram for this alloy. Okay, now from the diagram we can find out under sigma equals 400 megapascal, the corresponding epsilon, the strain, it's about 0.4, 0.04, 1, 2, 3, 4, yeah, 0.04. And now if we know the strain, we can further find out what is the delta L, right? Since strain equals delta L divided by the original length, therefore you can find delta L, it's epsilon times the original length. Here we can plug in the numbers for sigma, for epsilon, excuse me, 0.04 times original length 300, and what we get is, here is millimeter, and the answer would be 12 millimeter. So the resultant elongation gonna be 12 millimeter in this case. Yeah, if you have the stress strain diagram, it's easier to read out what is a strain without doing calculation. In this case, you cannot use the Hooke's law because we're not inside of the linear region anymore. And now let's look at the second problem. What's the total length under this load, sigma, and what is the total length L1? And here we just follow the steps we mentioned in the last example. L1 gonna be just the original length plus delta L. That's gonna be 312 millimeter. Okay, and okay, let's look at the third question. What is the total length L2 when the load is released? All right, then this is a question about elastic recovery after deformation. So make sure you follow